Hello everyone, I am M. Manasa from first year CSM SRIT. Welcome to my video presentation. Today I will be presenting on molecular orbital theory. It is commonly known as MOT. This theory provides a modern and accurate explanation for how atoms bond to form molecules. It is based on quantum mechanics and explains the distribution of electrons in molecules using molecular orbitals. Throughout this explanation, I will discuss how molecular orbitals are formed, the type of orbitals, bond order, molecular diagrams, and application of the theory. Introduction. Molecular orbital theory explains chemical bonding by considering electrons as delocalized over the entire molecule, unlike valency band theory, which restricts the electrons between two atoms. According to molecular orbital theory, when atoms come close, their atomic orbitals overlap and combine to form new orbitals called molecular orbitals. These orbitals extend over the whole molecule and influence its stability, magnetism, and electronic structure. MOT follows how quantum mechanical principles and gives more accurate results for many molecules. Let us know why molecular orbital theory is used. Valency band theory could not explain certain experimental observations. For example, oxygen is paramagnetic, but valency band theory predicted it to be diamagnetic. Also, some molecules like helium molecule does not exist, and a VBT could not justify this. Differences in bond lengths, bond energies, and magnetic properties were also not explained by VBT. Hence, MOT was developed. It successfully explains bond strength, bond order, magnetic behavior, electronic transitions, and even the stability of ions and excited states. Let's know about the basic principle of MOT. The core principle of MOT is the linear combination of atomic orbitals or LCAO. When two atomic orbitals combine, they produce two molecular orbitals, a bonding molecular orbital and another is anti-bonding molecular orbital. The bonding orbital is lower in energy due to constructive interface leading to stability. The antibonding orbital is higher in energy because of destructive interference, causing instability. Electrons fill these orbitals according to three rules. They are of Bohr principle. Lower energy orbitals fill first. The second one is Pauli's exclusion principle. Maximum two electrons with opposite spin are filled. The third one is Hund's rule. Electrons occupy orbitals singly before pairing. Coming to the formation of molecular orbitals form when atomic orbitals with the same symmetry and nearly equal energies overlap. The combination can be constructive, giving a bonding molecular orbital with high electron density between the nuclei, or it can be destructive, forming an antibonding molecular orbital with a node between the nuclei. The extent of overlap decides the strength of the bond. Greater the overlap, stronger the bonding orbital and higher the stability of the molecule. Types of molecular orbitals. There are two main types of molecular orbitals, sigma and pi. Sigma orbitals are formed by head-on or end-to-end overlap of s or p orbitals. These orbitals are symmetrical around the internuclear axis and usually form stronger bonds. Pi orbitals form lateral or side-by-side overlap of p orbitals. Their electron density lies above and below the internuclear axis, and these bonds are generally weaker than sigma bonds. In molecules with double or triple bonds, one sigma bond is formed while the others are pi bonds. Bond order. Bond order tells us the number of chemical bonds between atoms and indicates the molecule stability. It is calculated using the formula bond order is equal to half of number of electrons in bonding orbitals minus number of antibonding orbitals. If the bond order is greater than 0, the molecule is stable. If it is equal to 0, the molecule is unstable and does not exist. Higher bond order implies stronger bonding, shorter bond length, and high bond energy. Bond order examples. Consider H2. It has 2 electrons in a bonding orbital, giving a bond order of 1, meaning a single stable bond. In He2, we have 2 electrons in the bonding orbital and 2 in the antibonding orbital, giving a bond order of 0. That is why He2 does not exist. For O2, electrons fill up to the pi star antibonding orbitals, giving a bond order of 2. This also explains why O2 is paramagnetic due to 2 unpaired electrons in the pi star orbitals. These examples clearly show that MOT accurately predicts both bond stability and magnetic behavior. Molecular orbital diagram for 2p orbitals. In second period, diatomic molecules, the 2p orbitals have different energy ordering depending on the atomic number. For B2, C2 and N2, the order is pi 2p is less than sigma 2p. For O2 and F2, the order changes to sigma 2p is less than pi 2p. By filling electrons according to this order, we can determine each molecule's bond order and magnetic nature. For example, B2 has a bond order of 1 and is paramagnetic due to 2 unpaired electrons in pi 2p orbitals. In contrast, N2 has a bond order of 3 corresponding to a strong triple bond. Advantages of molecular orbital theory. MO theory has several advantages over earlier bonding theories. It gives accurate predictions about magnetic properties, bond order, stability, and bond length. It explains the existence of excited state, resonance stabilization, and electronic transitions. MOT can be applied to both simple diatomic molecule and complex polyatomic molecules. It is useful in spectroscopy, computational chemistry, and molecular design. Applications of molecular orbital theory. This theory is widely used in various branches of chemistry. In spectroscopy, it helps in understanding electronic transitions and absorption spectra. In inorganic chemistry, it explains bonding in coordination compounds. In organic chemistry, it predicts reactivity and the behavior of conjugated systems. MOT is also crucial in quantum chemistry, molecular modeling, semiconductor materials, and understanding atomicity. To summarize the molecular orbital theory, it describes the bonding by the formation of molecular orbitals from atomic orbital. It explains why molecules are stable or unstable based on bond order. It accurately predicts magnetic properties such as paramagnetism in oxygen. The theory provides a comprehensive quantum mechanical approach that is applicable to many types of molecules. MOT is therefore one of the most important theories in modern chemistry. And this is the end of my presentation. Thank you for your time.